Hey, welcome back to physics, friends. I've got a doozy for you today. Let's take it from the top and see what we can figure out. So, you wonder if a pulley 12 centimeters in diameter and weighing 2 kilograms has, okay, I got a lot of words here, okay? So the best approach for these kinds of problems is to take things one step at a time. For one, you wonder if a pulley, so here's my picture. I am drawing a pulley. Okay, 12 centimeters in diameter. I'm just going to write that down over here. Let's say D, 12 centimeters. And because I'm in physics, I'm not going to keep it in centimeters. I'm going to turn that into meters. I'm going to say 0.12 meters. Okay, 12 centimeters in diameter and weighing 2 kilograms. That's okay, so I'm going to put that here. M equals 2.0 kilograms. Good. Now we're good to move. Has its mass distributed uniformly through its volume, or if most of the mass is concentrated towards the center or around the edges, not uniform. Okay, so we're going to design an experiment to figure out if the density is uniform, or if it resembles more of a ring with most of the mass around the edges, or more of a sort of particle or sphere with most of the mass towards the center. Let's see. To find out, we're going to design an experiment in which we hang the pulley on a hook, wrap a string around it several times. Okay, we'll wrap a string around it several times. I guess we're going to hang something off of it. Sure enough, attach a 1 kilogram physics book to the string. So this is what we have going on here. That right there, that block physics book, is 1 kilogram. And now we're going to suspend the book 1 meter above the floor and observe that it takes 0.71 seconds to fall to the floor. Okay, so we have the floor. We know that this distance here, that is 1 meter. We know that the time to fall from here to there is going to be 0.71 seconds. Finally, what can you conclude about the mass distribution in the pulley? Seems kind of crazy that we'd even be able to conclude anything, but we can. Check it out. Let me first put to you a suggestion. Let me assume, okay, one, assume that the mass is uniform. Assume uniformity. If indeed the mass in this pulley is distributed uniform, then this here, this what I'm highlighting right now, is the situation we're talking about. I've copied over this diagram, which is a list of moment of inertias of different types of shapes. Okay, right here, 1/2 mr squared. This is true if my pulley is uniformly distributed. So, if I'm assuming that this is true, I know that I, moment of inertia, is equal to 1/2 mr squared. 1/2 mass times radius squared. And I can calculate that right away because I have these two things. Well, I have diameter. I know that radius is just half of diameter, so I'll do 1/2 of 2 kilograms times, I'm not going to use 0.12 meters, I'm going to use 0.06 meters squared because I want the radius. And I'm going to find out that again, the moment of inertia, if it's true that we have a uniform thing here, the moment of inertia should be 0.0036 kilogram meters squared. So why have I bothered to make this assumption? Because I think that there's another way to calculate moment of inertia. I think that's why they gave us this information about the 1 meter suspension and 0.71 seconds to fall to the floor. If we can calculate the moment of inertia another way and get the same moment of inertia as we just calculated, then we know the mass is uniform. If we get a greater moment of inertia, then we know that more of the mass must be concentrated toward the edges, right? That would mean that we have something more resembling a thin hoop or a ring. As you can see, the moment of inertia for a thin hoop is mr squared, whereas for a solid cylinder, it's 1/2 mr squared. if we do this calculation and we find that I is less than 0.0036 kilogram meter squared, we're probably dealing with something roughly like a particle or sphere. Most of the mass is concentrated toward the center, and we should have something on the order of 2/5 mr squared. 2/5 is less than 1/2 is less than m. So let's figure out an alternative way to calculate the moment of inertia and see what result we get. One relationship that I can use to describe the motion of the pulley and the block as it falls to the ground is this: conservation of energy. Energy initial equals energy final. And what I'm going to say is that initially the block had some potential energy. So PEB, potential energy of the block. Potential energy because it was a certain distance off the ground. It's gravitational potential energy. Equals E final. Well, what goes on after this thing has dropped? So right here, the moment before we hit the ground, we have some velocity. And on top of that, we've caused the pulley to spin somewhat. So here's what I'm going to say. I'm going to say that the potential energy of the block initially is going to be equal to the kinetic energy, the total kinetic energy of the system. That's going to be KER, rotational kinetic energy of the pulley, plus KET, or translational kinetic energy of the block. Now I'm going to replace each of these energy symbols with formulas. I have mgh for the initial potential energy, all of which is going to turn into rotational 1/2 I omega squared, and translational kinetic energy 1/2 mv squared. This is talking about the block, this is talking about the pulley only. And what I'm interested in finding, and make it real clear, is this. We should have enough information to figure out what this term is and compare it to this term that we just got. So I want to solve this equation for the unknown variable I. Let's see what I know. Let's see, m, that would be the mass of the book. I've got that. G, that's acceleration due to gravity. I know that. I know the height. It's 1 meter. This guy, omega, I don't know. But again, we have the mass popping up again, and another thing I don't know, the terminal or final velocity of the book before it hits the ground. Fine. Here is how I'm going to figure it out. I'm going to say that the acceleration, well, I'm going to use a kinematic equation. I'll say d equals v0t plus 1/2 at squared, something we should be very familiar with at this point in physics. I know that we have no initial velocity, so d is going to be equal to 1/2 at squared. The thing is, I know distance and I know time, so I'm going to figure out acceleration, linear acceleration of the block. That means a is going to be dt squared, d divided by t squared times 2. Okay, that's going to give me an acceleration of 3.96 meters per second squared. Now I can use another kinematic equation to grab my velocity. So let me do that. Let me box that off. That didn't go that well. I'm going to block that off, and I'm going to figure out v now, velocity. Well, I know that v equals v0 plus at. It's another kinematic equation. Still no initial velocity. V is equal to at. We just found a. We still know t. Now it turns out that v is equal to 2.817 meters per second. Good. Now I have found this. But what about omega? Okay, another real simple substitution I'm going to use. I'm just going to say that omega, actually I'm going to do it over here so I still have room. I'm going to say that omega, that's just v over r. That's from our relationships between rotational and linear quantities. Omega should be 46.6 0.95 radians per second. That's going to be 2.817 divided by the radius of 0.06. Okay, that's the last thing I need. We're ready to substitute and solve this equation. So what we've got, if I just replace everything wholesale, we're going to get mass 1 times G, 9.8, times H, 1, times 1/2, which I'm just going to say is 0.5 for ease of putting into the calculator, times I, okay, times omega, 46.95 squared, plus 0.5, times my mass, that's the book again, times my V, oh no, I'm going to run out of space, 2.817, that's okay, who cares, 2.817 meters per second squared. And I'm going to do all this work and I'm going to solve for I. Check it for yourself, but it turns out that I is going to be 0.00529 kilogram meters squared. And look at that. It turns out that the I is when we calculate using the motion is different than when we calculate it using the formula, which means our assumption was incorrect, and most likely we have something with more mass concentrated around the outside, the outer circumference of the of the pulley.